Okay, this is the final chapter on optimal emission reduction. I talked about the legal situation, international agreements. I talked about cost-benefit analysis and highlighted how the two contradict each other quite heavily. Now I'm going to change gears again and talk about co-benefits or secondary benefits. What happens to climate policy if climate policy affects other environmental problems as well? I'm going to start with the motivation. Why is this important? I'm going to talk about independent policy and then about interdependent policies. This part of the lecture is a bit more technical than most of the other things that you've seen so far. What you're looking at here is a pretty old cartoon. I think it's 1994 by Joel Pett of USA Today. And there's some sort of climate conference going on, and there's a speaker there, and then this middle-aged white guy, and it's always a middle-aged white guy, stands up and said, what if climate is a big hoax and we create a better world for nothing? And then the speaker points at all the other good things that supposedly come from climate policy, like energy independence, preservation of rainforests, sustainability, green jobs, livable cities, renewables, clean air, clean water, healthy children, and so on and so forth. And the question, or the suggestion that is made by this cartoon, and it's a widespread belief in environmental circles that this is indeed true. The suggestion that is created here that even if climate change is not a problem, then we would still want to reduce greenhouse gas emissions. And the question that I'm going to ask is this true? I'm going to consider two problems, two types of emissions, G for greenhouse gases and A for air pollutants. And instead of talking about emissions, I'm always going to talk about emission reductions. Sorry. So there's benefits B of emission reduction, that is just an aggregate of how much emissions we reduce for air pollution, A, and how much emissions we reduce for greenhouse gases, G, and those are weighted by parameters alpha and chi. Then this problem becomes interesting because the emission control, R for greenhouse gas emission reduction and S for air pollution emission reduction, affect both. So G, how much CO2 or greenhouse gases are reduced, depends on R, the targeted policy for climate, but also depends on S, the policy that targets air pollution. And similarly, air pollution reduction A depends on policy targeted at air pollution S, but also depends on policy targeted at climate change R. And we introduce a set of parameters there as well. The cost of emission reduction are assumed to be quadratic. That is, the more we do of S, the more expensive it gets, and that goes up more than linear. And the same, the more we do in R, the more we cut our greenhouse gases, the more expensive it gets, and also at the margin. So that is the fourth equation that you see. Now, the benefits is alpha A plus chi G, but we know G and we know A, so we simply substitute that in, reworking the benefits. And then we have the equation that you see there, alpha sigma S plus tau R plus chi pi S plus rho R, and we rework that into a linear expression in S and R by rearranging and combining parameters. So let's just repeat those equations. We have the benefits, we have the costs, both equations you've seen before, and now the optimal control for R follows from equating the marginal costs to the marginal benefits. So dB dr is alpha tau plus chi rho, and the CDR is lambda rho. So rho prime, the optimal amount of emission control for optimal control for climate policy depends on or equals chi rho over lambda plus alpha tau over lambda. And in words, that means essentially that we want to control climate change, and that depends on our concern for climate, that is the chi, times the effect of our climate policy on climate, rho, and that then needs to be divided by the costs of climate policy, lambda. And this is your standard cost-benefit analysis of climate change. But if we are also concerned about air pollution, then we should add to our optimal control rate for climate our concern about air pollution, alpha, times the effect of climate policy on air pollution, tau, over the costs of climate policy. And obviously, if our climate policy does not affect air pollution, then tau is 0, and we do the standard cost-benefit analysis for climate. But if we do affect, through climate policy, if we do affect air pollution, then we should do more, presumably, on our climate front. Graphically, that looks as follows. So this is a linear quadratic problem. The cost function is quadratic, so the marginal cost function is linear, and that's the brown line that you see. But the benefit function is linear, and therefore its marginal is a constant, and those are the green lines that you see. So if we just care about climate, and that's the only thing, only problem that we worry about, then that is the green line that you see in the middle, and we would cut emissions by the amount where the green line hits the brown line. Now the purple line that you're looking at is the marginal secondary benefits, that is how much we care about air pollution times how much air pollution is affected by climate policy. And if this equation here is true, then we should add that. And what you see is then our total benefit is the primary benefit, the benefit of reducing climate change, plus the secondary benefit, the benefit of reducing air pollution, and in total we would do more. There's also a light green line where I subtract the two. And the reason for that is that who says that alpha times tau is positive? If alpha times tau is greater than 0, then indeed we should add things. And air pollution is a real problem, so there's absolutely no reason to assume that alpha could be negative, that is, we would like to poison our children and our lungs. That is not the case. But it is not necessarily the case that the tau is positive. And one example where the tau is positive, where it's very clearly the case that if you reduce greenhouse gas emissions, you also reduce air pollution, is if you switch from coal burning to gas burning in power plants. Because coal emits a lot of CO2, much more than gas emits per kilowatt hour of electricity generated. But coal also contains a lot of sulfur and other imperfections in the fuel, whereas gas tends to be much purer, and typically the gas that you burn is just gas, and there's no other substances in there, and therefore it burns clean and it just turns to CO2 and H2O. Not the case for coal. So if your climate policy is to replace coal-fired electricity by gas-fired electricity, then you solve both problems at once, and therefore you should work harder on your climate policy because you also avoid air pollution. However, there's also cases where your tau is negative, and the best example there is a switch from petrol to diesel cars. Now, diesel cars burn a lot more efficiently than petrol cars do, and that means that per kilometer traveled, a diesel car emits less CO2 than a petrol car, all else being equal. However, a lot of air pollutants come out of diesel cars rather than petrol cars, and its particular particulates are a much bigger problem for diesel cars than for petrol cars. So in this particular case, what you find is that from a climate perspective, you would want to switch from petrol to diesel, but from an air pollution perspective, you would want to switch from diesel to petrol. And that means that your tau is negative, and therefore, because this climate policy increases air pollution, you want to work less hard on your climate policy. And the alpha tau is negative, and you need to subtract this from your benefits, and therefore the optimum is less. Now, to return to Joel Pett's cartoon and the middle-aged white man saying climate change is a hoax, that essentially means that we don't care about climate, either because climate is not real or perhaps its impacts are negligible. And both cases, the chi, how much we care about climate, would be zero. And what you see, if your chi is zero, then you still have your alpha tau over lambda. So even if climate change is a hoax and your tau is positive, then you still would want to reduce your CO2 emissions. So in that sense, Joel Pett is right, or the suggestion in his cartoon is right. But of course, if your tau is negative, then you actually would want to subsidize greenhouse gas emissions, because that would reduce air pollution. So that is the simple case. I focused on optimal emission reduction for climate change because that's the subject of the lecture. The problem is entirely symmetric. So the same story holds for the optimal control of air pollution, where again, whether or not you want to increase your air pollution policy or decrease your air pollution policy depends completely on the sign of your parameter pi, and if pi is positive, then you would want to work harder on your air pollution. And an example of a positive pi is a switch from coal to gas. We actually switched from coal to gas also because of our concerns for air pollution, and if it's positive in one direction, then it's also positive in the other direction. But there's also examples of negative pi's, and actually more prominent examples of negative pi's, because if you think back of the 70s and the 80s, before a lot of you guys were born, we were deeply worried about acid rain, and we solved acid rain problems in Europe, in North America and Japan by putting scrubbers on smokestacks. Those are essentially, a lot of acid rain came out of coal-fired power plants. It was essentially sulfur that was an impurity in the coal that was burned. And rather than switching away from coal to gas or switching away from coal to wind or solar, what people did was they removed the sulfur from the flue gas. So you still burn the coal, but instead of dumping the sulfur into the atmosphere, you remove the sulfur in the factory before it enters the atmosphere. Those are called scrubbers. They are placed on smokestacks, or rather under smokestacks. The problem with scrubber plants is that they're expensive. They increase the capital cost of a power plant quite considerably, but they also take a lot of energy. So this is a chemical process, but you need to stick in a lot of energy to make it work. And about a third of the output of a power plant is not delivered to the grid, but is delivered to the scrubbers. And that means that to get the same amount of electricity to the grid, you need to generate more electricity, you need to burn more coal. So your CO2 emissions are going up, but your SO2 emissions are going down, and that means that your pi is negative. And that means that if you are worried about air pollution but also concerned about climate change, then you should work less hard on your air pollution policy. So, to sum up this part, if greenhouse gas emission reduction helps solve other problems like air pollution, energy security, then we should do more of it. But in case it makes those other problems worse, then perhaps we should be less enthusiastic about greenhouse gas emission reduction. Now, this setup that I just showed you was the simplest possible. And what I'm going to do now is introduce another interaction between the two policies. So the benefits of emission reduction stay the same, alpha A plus chi G. The emission controls for greenhouse gases, G, stays the same, that's still pi s plus rho r. But our emission controls for air pollution, I introduce an interactive term. So it was sigma s plus tau r. It is now sigma s plus tau r minus psi times r times s. So a simple interaction term between r and s in one of the equations. If we rework that equation, then A becomes sigma s plus tau minus psi s times r. And the way to read this is that the harder you work on your emission controls for air pollution, the lower the effect of greenhouse gas emission control is on air pollution. That is, if through your air pollution problem you can make the air pollution go away, then you don't need to worry about the implications of your climate policy on your air pollution, because you have already solved it, right? So that is how to read this particular equation, and that's the interpretation that I'm going to give to it. The cost of emission reduction stay the same, the quadratic equation that we saw before. We plug the emission control equations into the benefits equations to see the reworked benefits that you see there. And I'm actually going to use the top equation rather than the bottom equation. And of course, the things that are new relative to what we saw before are the terms in red. So we have a benefit equation and we have a cost equation. We can work out the optimal control for greenhouse gases R. That's the BDR must equal the CDR, and the new term that pops up, what used to be linear, we now have that R depends also on alpha psi times S. So emission control for R becomes alpha tau plus chi rho over lambda, and that is exactly what we had before, minus alpha psi over lambda times S. So the more we do in S, assuming that all these parameters are positive, the less we need to do about R, because essentially we are taking away the air pollution problem and therefore taking away the co-benefits of our air pollution control on the co-benefits of our greenhouse gas emission control on our air pollution problem. And as things are entirely symmetric, the same happens for our emission control for air pollutants S. You need to subtract the term alpha psi over kappa times R. So the harder we work on greenhouse gas emission control, the less we need to worry about our air pollution problem because of the spillovers, the presumably positive spillovers. Graphically, that looks as follows. So we have the brown curve, which is the same as it used to be, and it's just a linearly increasing function. We have our primary benefit, which is the lowest line, and then we have the secondary benefit that is the same as it used to be if S is 0, if there's no air pollution policy. If S is 0 in the equation that you see there, then R is simply alpha tau plus chi rho over lambda, and that is exactly as it was before. But now if S is not 0 and we are working to reduce our air pollution problem, then the secondary benefit shrinks and we go from the top line to the middle line, and that then implies that our optimal emissions are still, our optimal emission control is still higher than if there were no co-benefits, but it's lower than if there's co-benefits and no air pollution policy, right? So it lies somewhere in between. Now this overlooks one particular issue, and that is that our R depends on S and our S depends on R. So the two equations that you see there are not the solution. Fortunately, what we have here is two linear equations with two unknown variables, so we can solve this. And the solution to this is the term that you see at the very bottom. And then in the slides that are on Canvas, you can actually rework. You can see the workings of this, how you get from R and S that depend on each other to your R prime. What you need to do is still subtract your alpha psi, but you need to moderate that by the term alpha sigma plus chi pi. But most importantly, you also need to moderate the what is below the division. That is no longer a lambda, but that becomes a lambda kappa minus alpha squared psi squared. So there's a lot of additional things that are there. There's also a kappa that pops up above the dividing line, but there's also a kappa that pops up below it. So those two cancel if your psi is 0. That is, there's no cross term. And then we're back to the original solution. Now, how does this look graphically? Essentially, you divide by a smaller number, and that means that your marginal cost curve becomes less steep. That is de facto what is going on. So there's now three movements. First, you go from your marginal primary benefit to your marginal primary benefit plus your marginal secondary benefit, assuming that there is no air pollution emission control, and that means that you need to work harder on your greenhouse gases. But then the answer is no, 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 no. We also have air pollution policy, and therefore I need to worry less about, or I need to I need to worry less about air pollution because of air pollution problem, because of air pollution policy. But it also means, of course, that the benefit of further reducing your air pollution falls because you've taken away part of the problem, right? So you go from the top green line to the middle green line, and you reduce your emission control again. But then, of course, what happens if you reduce your greenhouse gas emission control? Then you become more worried about your air pollution problem again, and you want to increase your emission control again. And that's the shift in the brown line, in the marginal cost of emission reduction. And then you want to do more about your greenhouse gases again. And of course those things iterate, because your air pollution policy, your optimal air pollution policy, depends on your greenhouse gas, on your climate policy, and your climate policy depends on your air pollution policy, and you can iterate that, but fortunately we can solve that. And the effect is a shift in that particular curve, and you want to do more again. So these interactions can be a bit tricky to think through. So to sum up, if greenhouse gas emission reduction helps to solve other problems, then we should do more of it. But if greenhouse gas emission reduction helps to make other problems worse, then we should do less of it. And of course, how much we want to adjust our greenhouse gas emission reduction policy also critically depends on what policies are directly aimed at those secondary issues that we are also concerned about. So there is no clear and straight answer. It is not the case that if there is another problem you worry about, you should work harder on climate policy. It may go either way, and of course if there is an alternative solution, or if there is a solution to the other things that you worry about, then they don't affect your optimal climate policy much.